good morning again everybody, and let us continue our discussion of fabrication of micro cutting tools. In the last class we have seen different processes like a laser beam process, electric discharge machining process and focused ion beam process. So that by these particular processes we can fabricate different geometry of the cutting tool with a different type of diameters. So let us continue this further discussion, and there is still one more process left, that is called the ELID, and that is called electrolytic in process dressing process. Electrolytic in process dressing, right. So, now what is the objective of this particular process? That the objective is that the protrusion of the grains should be remain constant throughout the by the in process dressing. So, when you do this is something like a grinding process only, but it has an in process dressing facility, because what we do in the grinding operation, that when the there is a wheel loading happens, or when there is a abrasive particles become dull, then what we do, that we do some type of dressing operation here. So, by dressing what we are doing, we are resharpening the abrasive particles, so that we can actually create some new sharp edges onto the wheel, and then wheel can be efficiently remove the material. But then we do mostly in the offline, that means we stop the machine and then we do something out of that. But here the same thing what we are doing, it is in process dressing. So, let us see what that mean. So, this is the setup, and now what we are doing here, that we have a grinding wheel, but here the grinding wheel is a metallic grinding wheel, because we have to create one type of electrochemical circuit here. So, this is the anode we can work, because we want to remove material from that part, and this is the copper electrode, and it is a cathode connected with this, and this particular location you are doing machining operation, and at this particular location what we are doing in process dressing part. And this is the oxide layer, that means the bonding material is the oxide material. Then you can use the diamond particle or any other particles also. Then this is the way it is happening, that at one location it is doing machining here, and at the other location what it is doing, it is doing dressing. So, continuously you are getting the resharpening of the edges, and every time the protrusion remains constant, and you are getting the good machining capability. So, this is the way this particular process works. So, what is here, that this is the initial topography of the grinding wheel after dressing. So, you have dressed it, and these are the particles. Now, what is happening, that because of this electrolysis, or what is happening, that it creates some oxide layer on this. So, this is the oxide, what material we are using here, that is material is oxide. So, that creates a oxide film here. So, this is the oxide film, and because of this oxide is actually very weak compared to the parent oxide material. So, when you perform the ELID operation, what is happening, that it will remove this oxide film, and along with that it will actually dull out these particular particles also, correct. So, now once it reaches one particular oxide film formation, then this ELID will not continue, because it will take lot of time to reach to the fresh surface. But when you do machining at that time, so at that time what is happening, that you are removing or you are deforming this particular oxide film during the grinding operation. So, the thickness of this oxide film is reduced. So, once it is reduced, then what is happening, that you are getting a protrusion of this particle again here, and now the thickness is less, right. So, now once you get this particular less thickness, then again your ELID cycle will start, and then it will again further create the oxide film. You continue operation with this oxide film, it will reduce the oxide film by grinding operation, again goes to this location. This will continue till you consume the grinding wheel. So, what is here objective, that every time you are getting a constant protrusion of the grain, and that is the good reason for using this particular process for fabrication of a different type of shapes on the micro cutting tool. Right. So, these are the different shapes. So, it is a rectangular type of tool, this is almost a square type, but a spherical surface at the two location, and this is the square type of tool. So, now you can see that these shapes are almost similar to the surface what we are getting into the focused ion beam machining, but focused ion beam machine is actually more precise process compared to this thing, because we have seen that grinding that still there is a physical contact, and because of that you can see this is 100 microns. So, diameter size of this one side bigger size is more than 2 micron or 200 micron, something like that. And similar way here it is the dimension is 100 microns. So, this may be considered 70 micron or something. So, going down and down is very difficult, but still this is reasonable size of the cutting tool which can be fabricated by ELID process. Right. So, these are the different processes. Now, let us discuss that what are the different issues with the micro cutting tool, because once you fabricate the cutting tool, then you have to use this cutting tool for final operation. So, when you operate at the time, you have to take care of some of the things. So, let us see this thing. So, cutting force and the tool pressure create the whole new realm of the problem, because in earlier case when you are using a micro cutting tool or bigger size of cutting tool, we actually do not pay more attention to the breakage of the cutting tool, but we pay attention to the wear of the cutting tool by studying the forces and the pressure whatever it is creating on the part. Any variation in the axial position during the cut can be disastrous, because now you can see that we have seen in the geometric error lectures where we have seen that if there is a shifting into the x, y or z direction, your tool movement will not be a straight line. You may get the different type of additional movement, and that additional movement will actually create a problem, and it will create a uneven pressure or the very high fluctuation of the forces onto the cutting tool, and that is very disastrous, and it will break the cutting tool instantly. The spindle must be stable and minimize thermal expansion, tool change variation and the vibration, because we have seen in the spindle also that what are the different ways you can actually use the spindle. So, first thing is that it should be stable in the sense that when you operate in the high speed regime, at that time there should not be any type of deformation within the spindle. Thermal expansion is also, we have seen that how thermal expansion play important role there. So, we can go with the air bearing, then thermal expansion will be very less. If you go with the ball bearing or the roller bearing, you will get some thermal expansion because of the friction and the height generation. Tool change variation, that is also important, because we are not using same tool for all the operation. After certain operation you have to change the tool. So, what is the variation in the tolerances when you fit one tool and then you remove and another fit another tool? What are the problem associated with those things? And finally, the vibration, because vibration also important, because what type of ball bearing you are using, what type of preloading we are using, depending on that you can actually control the vibration, and those things we have discussed in detail. Vibration or run out at the tool tip, because and this affect the surface and accuracy. Now, you can see there are many ways we can actually see this thing. Now, see this is our cutting tool holder and our tool is held in this particular location, and this is the cutting tool or cutting edge, right. So, our objective is that we are using this particular portion for machining. So, this is the portion which we are using for machining. Remaining part is just for the support only, right. So, now if you see that if you have a vibration or run out, now let us consider run out only. So, if you are run out, then what is happening, that suppose this is the axis of the spindle and this is the axis of the cutting tool. Now, let us see something like this, correct. So, now if you see that the run out here it is very less, right. Consider it is, if it is a 10 micron, but when you see at this particular level that how much it is here, that will be 10 multiplied by some x, that depends on what is the total length of the cutting tool. So, this particular run out, what is important, that we have to measure the run out at the tool tip, not to this location, because here you will get some run out, but this reading will be misleading. So, that is the reason that always measure the run out at the cutting edge, because that is the actual run out and that will play important role in the machining zone. So, that will directly affect your surface finish and the accuracy, right. Problem with micro tool, that amount of force associated with the removing of material at the particular level. Now, that means whatever material you are removing from that, where this material is going. So, if it is coming out as a chip, that how efficiently chip is created and how efficient it is coming out of the machining zone. So, that will decide that how much amount of forces are actually you are playing with this particular material. So, one of the main problem or limiting problem is the reduced stiffness with the tiny sizes, because when you go smaller and smaller, now grain size of that cutting tool also play important role. You cannot use a bigger size of cutting tool when the diameter itself is 100 micron or something. You have to go with a micron size or the sub-micron or nanometer size of grain size, so that more amount of grains available and you can get the little bit higher stiffness. But still the stiffness is not high as compared to the conventional shape. So, that is the limiting factor. You cannot reduce the size beyond a certain limit, right. Another problem, the tool does not gradually wear until it causes undesirable surface effect, rather the tool breaks quickly as it becomes worn or reaches to the bending limit or bending strength of the limit. So, now mostly if you do conventional machining operation, what is our objective? We study the tool wear, right, because we know that the breakage of the tool will take more time compared to the wear of the tool, but it is actually reverse into the micro cutting, that here you can easily reach that particular limit of the breaking strength compared to the study of the wear. So, in the study of micro machining, what is our objective? Our objective should be to reduce the breakage of the cutting tool, not to the wear, because you can study the wear only when you avoid the breakage of the cutting tool. So, here that is what is problem. So, our here that is when the tool breakage is the more likely outcome. So, mostly our objective is to save the tool first and then you do the wear characteristic or the wear study to show that what is the total acceptable life of the cutting tool. So, what happened, why this thing happened? Because when you cut with a dull cutting edge, then your cutting forces will be very high and stresses exceed the strength of the small diameter cutting tool, and then it will fracture. So, this is the way, this is the reason what is happening because of what is happening with the cutting tool of the this particular size. Now, first thing, that it is impossible to determine whether the tool has been broken or broken by the unassisted rear. So, now we know that size of the cutting tool is very small. So, you cannot get anything in terms of some noise signal or some type of process signal that what is happening, whether tool is there or not. So, what is problem because of that? That suppose you are starting a 8 hours of cycle and your tool is broken in the first minute itself, and you do not have any type of what we can say the feedback devices or some type of what we can say that it is some type of accessories or the force measurement system in such a way that it will give you this type of signal. So, you are starting a 8-hour cycle and within the 1 minute your tool is broken, but you will get that information once you complete the 8-hour of cycle, right. So, once you do that, the tool is broken and you have already wasted 8 hours of time. So, what is things what we have to do here, that we have to invest something onto the tool monitoring or the process monitoring system. So, if you install one sensor or 3-axis sensor, that is may you consider as a piezoelectric sensor or some type of acoustic emission sensor, which will continuously give the signal of the machining forces, right, because we know that whenever there is a material removal, you will get some force reading. If you get force reading, you are sure that your tool is in contact with the workpiece. So, you have to invest not onto the machine, but you have to invest something on the auxiliary accessories. Mostly it is related to the sensing of the cutting process, that is by means of some type of sensors. So, another thing is what we require, we need hard tool or the tough tool, right. So, what we need the actually compromise between the hardness and the toughness. So, it requires an advantageous combination of hardness as well as toughness. So, how you can get the both the things done, that means you have it can be achieved by formulating a mix of extremely fine grain of the tungsten and the cobalt, because we know that tungsten carbide we are using and then cobalt is the binder of that particular material. Then hardness of the solid carbide enables it to cut well formed chips in difficult to machine material while resisting the chipping and the cutting edge. So, what is the use of this carbide? Carbide will actually, it is very hard material. So, it will actually resist the cutting edges, that means cutting edge sharpness will retain for a longer time, and toughness of the material helps in the shaft resist the breakage from the cutting forces and keeps the tool from vibrating. So, why we need the toughness also here? Because we do not want to break this thing, because hard material will break very easily, but if you use toughness here, that means even if there is a little bit amount of bending or vibration, it will actually retain that particular thing. So, what is the required? We need a balance of hardness and the toughness, because both the things cannot be achieved simultaneously. So, you have to sacrifice the hardness by putting some more toughness, so that tool will not be broken during the vibration or some type of high amount of bending load. So, that is the way we have to think about the what should be the composition of the tungsten carbide tool in such a way that you can get the required properties done. So, there are different issues of the micro bracket. What are the 4 issues? So, these 4 issues are the mostly related to the tool setting and all this. So, smaller the tool, tools are small and delicate. So, there is a high tendency of breakage. So, first thing is the runout. So, runout is the biggest issue compared to all other issues, because we know that this avoiding this thing is very difficult, because we are doing lot of setup and settings during the different positions. So, spindle run out at actual RPM when measured against the spindle taper, right. So, this is what is we are talking about, the spindle run out. That is another thing is the tool holder and the collet run out, right. So, now if you see this particular thing, now it has a 2 things. First thing is the when you are holding the this is the tool and then you are holding this tool into the tool holder. Now, see that the axis of the tool holder and the axis of your cutting tools are not coinciding. So, this is called the alignment error. So, this alignment error can be reduced by using a proper tool holder, or we can use some type of spindle without any tool holder also. So, those things are available, we will see in the next few slides. So, this is called the tool holder and the collet run out, right. So, this is the tool holder, there is a collet available here, and on the collet you are putting the cutting tool. So, this is the first thing which is happening between the tool holder and the collet, and this is the fluid run out related to the shank side. Now, this is the second one. You can see here this one, this is the cutting tool and this is the shank. Okay. So, what happens that when you fabricate this particular tool, at that time we have seen lot of different processes, but if those processes are not that much precise or the high resolution processes, then what is happening that you will get one under run out with respect to the shank with the fluid. So, that is the within the cutting. We are not talking about any type of alignment of this, but this is the manufacturing error. Right. So, what is happening here, the tool may not be made perfectly symmetrical and concentric with the shaft. So, right now if you see here that this tool is not concentric with the shank diameter, right. The tool's fluids may have the 10 micron or more run out related to the tool shank. So, that depends on which type of manufacturing process you are using, and depending on that you will get the different tool run out, that means the run out with respect to the fluid and the shank. So, you can see that these are the different ways by which you can get the run out into the system, and so that you have to find some of the ways by which you can reduce the alignment error, and you have to also make sure that your whatever process you are using for fabrication of this cutting tool, those processes are very finely tuned, otherwise you will end up with this type of cutting tool errors. Right. So, let us continue this. All of these source of errors takes up. Now, whatever we have seen here, that there are 2 errors, one is the alignment error and there is the manufacturing error, but those 2 things will not play separately role, because both the things will be actually combined with each other and it will stack up, and total run out will be very high at the later stage. So, run out will be additive to the chip load. So, now what is happening that one tool has a run out at both the locations, the alignment run out and the manufacturing run out, then because of that your total run out will be extremely high, and it will directly affect the chip load, that how much chip is removed in a by one rotation or by one fluid. So, what is the thumb rule, that to keep the run out from becoming the limiting factor, it needs to be kept with keep to not more than 10% of the cutter diameter, right. So, when you are talking about the diameter of a 100 micron, then let us say consider that it should not be more than 10 micron of run out. So, now when you are talking about 250 micron diameter, then what is that, your acceptable run out is 25 micron. So, that is not very difficult to get the run out 25 micron, but when you go down and down, let us consider your diameter is 25 micron now. So, by this thumb rule, what is our objective, that now the total run out from all the sources should not be more than 2.5 micron, and that is very demanding. So, now you can see that going smaller and smaller in the diameter, then what is happening, that the requirement of the precision of the fabrication process, and then the alignment process, everything actually become more and more demanding, and those things should be very precise, so that we can work within this particular domain, so that runout can be minimized. Now you can see if it is a 2.5 micron runout, then 25 micron plus 5 micron, you consider plus or minus means 2.5 on both the sides, it will be 5 micron. So you cannot create any features less than 30 micron. Still your, even though your diameter is the 25 micron, right. So this is the problem with the runout. So what are the different type of runout? One is called the angular total indicator runout. So this is called angular runout, right. So now you have angle. So now there is always one point through which the both axes are actually separating. So this is called angular because it has some angle. So this is called angular runout. It may happen between the spindle to the collet also, and from collet to the workpiece also. So what are the reasons for this thing? That poorly aligned central collet bore. So when you are actually making the system for this collet, it may also create a problem, because if that collet is not actually aligned with exactly with that one spindle taper, because if you are using some type of mechanical, that ISO or BT kind of thing, then what will happen? Because of the friction, there is a wear of the taper also, and then the straightness and the eccentricity of that taper will be lost, and then you will end up with the angular thing. Debris between the collet and the spindle bore taper. So if some debris is there, then you will not get a full contact around the taper, and because of that you will get this alignment around. So when you do machining with this type of things, what is going to happen? That you, instead of a circle part, what you are getting, you will get some type of oval type of geometry. And before you get oval type, sometimes very high chance that your tool will be broken, because at one location it is getting more stress compared to the other location. And there is another one is called the radial run, total indicator run. In this case, what is happening? That it is not actually angle, but it is a complete shifting of the of the two axes. So this is, you consider the spindle axis, and this is called the tool axis. So there is a parallel thing. So this is why it is called the radial runout. If you do operation with this thing, suppose your diameter is 25 micron, then you will get the diameter of 30 micron if this thing is at 2.5 micron, right. But still that is mostly not happening, because that much 2.5 micron itself is sometimes more than enough to break your tool. So what are the reasons for this thing? That an offset collet bore, that your collet bore itself is offset, you are not actually getting this thing with respect to the spindle axis. Then mounting a tool with a shank diameter smaller than the minimum diameter of the collet gripping range. So now everywhere, now if you see this type of ER collet, so ER collet has a different thing here. So now here what is happening here, that ER collet has a different type of gripper. So these are the gripper which will hold the cutting tool at the later stage. This way it is like, and our cutting tool actually placed in between these two. So when you are holding, now this particular thing is given by ER 12, 13, ER 14, 15, something like this, right. So your diameter, whatever diameter of this particular tool, that the shank diameter should be within this part, right. Now if you say that you are using ER 12, 13 and you are using a shank diameter, consider you are using shank diameter of 11 or something, right. So what is happening in this particular case, that your tool is actually gripped by the a few this particular support only, but it is not actually matching at the center, because ultimately when it is gripping from all the sides, at that time it will remain at the center. So it will make sure that it is at the center. But when your tool shank diameter is smaller than the minimum diameter range of this, because range is 12 to 13, but your diameter is 11 here. So it will be gripped by a few these particular grippers only, but not from the all the location, and then you are end up with the radial runout. So, what is problem with this particular thing? Now you can see that this is the run out. Now you can see that when it rotates, at that time your dial gauge is moving at different location. Now this particular tool is a run out, right. Now we are using this tool for doing a drilling operation or the cutting operation. What is happening here at this location, that only one cutting edge will do all the operation, other cutting edge will not come into action at all. Now you can see this particular cutting edge completely free. Because of this run out, at bottom and all the work is done by the one cutting edge. What is the problem because of that? That first thing is that your tool life will be sacrificed, that you cannot use this tool for a longer time, because whatever the chip load capacity or chip load calculation you have done, this all the thing is done by considering that your both the cutting edge will participate into the machining operation, but that is not happening here. Only one cutting edge is taking all the load of that, and that cutting edge will quickly worn out, and within a small duration you have to replace this particular tool. Right, this is what is happening at this location. And what is happening here, that you are also getting a different type of surface here, and if you do same continuously, then what is happening, that you are end up with the burr formation also, because you know that before it is reaching to the end surface, your tool that edge is already worn out, and that worn edge, we know that the cutting edge radius is very high now, and because of that you are not maintaining the uncut chip thickness to the cutting edge radius for that relation, and because of that efficient material removal will not take place. So, there are two issues, one is on the material side, that means you are end up with the burr formation and some type of material integrity issue. Another is on the tool side, that your tool life is very short in this particular case when there is a run out. So, what are the ways you can actually reduce this particular thing? The one thing is called the direct tool change type of spindle. Now, you can say this particular spindle, it does not have a collet. So, this particular thing actually you can eliminate completely the tool holder. So, the tool whatever you have, it is directly fitting into the spindle. So, by that way you can reduce the total run out, right. So, these spindles are readily available, and by that way, because what is our objective? Our objective is to reduce the minimum joint, right. So, if you reduce the number of joints, then what is happening here, that we can actually going in a more safer zone, where we can we ensure that number of joints are less. So, the possibility of a cumulative run out is also less, because you are completely avoiding tool holder, that means tool holder to the collet, it is completely avoided, and then only you are left with the fabrication issue of the cutting tool. So, this is one of the way, the direct tool change type of spindle available, where you can actually get the things done very easily. Then how to measure? So, there are different type of sensors available, by which you can actually do measurement of the run out. So, this is the capacitance type. So, here this is the spindle and motor, and you are putting a capacitive sensor here, and you can put at any location depending on the measurement of the run out, and then you rotate your spindle. So, when you rotate your spindle, what is happening, that your capacitance will change, because now we know that your capacitive one plate is here and this is the under workpiece, and now consider this is the run out portion. So, now your spindle will move in this and this direction, correct. So, when it is very near to it, at that time it will actually give one type of signal here, and when it is away from that, it will give another signal, right. So, within that rotation, what is happening, that this is in microsecond. So, when you rotate it, at that time it will give you one signal. So, this particular thing will tell you that what is the radial run out. So, this is in this direction, correct. So, if you see, this is moving within a plus or minus 5 micron, almost something like that. So, this much amount is the run out. So, run out is the 5 micron here. So, this is about the radial part. Now, this is about the axial part, because we have to see about the z axis also. If you are doing machining with a constant depth of cut, if you do not know that what is your axial run out, then what is happening, that you will not get that constant depth of cut, but you will get a variable part. But here what is happening, that if you put the capacitance sensor here, then whatever the difference in this thing is there, then it will be actually captured by this particular axial displacement, which is in micron. So, now you can see this particular signal will tell you that you have axial displacement around 25 micron. Now, you can see that if you are machining with this particular surface, and now you have a 25 micron is a radial and something 5 micron at that particular diameter. So, if you are moving with a plus or minus 5 micron, that means you are actually working with a 10 micron of range, right. So, any diameter more than less than diameter of the actual cutting tool plus this thing you cannot make, right. So, that is not possible here. Other than that, there is a variation in the depth also. You will get a different depth at the different location depending on this particular band. Whatever this band is, that much variation you will get at the Z direction. So, by this way there are different other sensors are also available by which you can do measurement. Mostly conventional way is the put the dial gauge with a 1 micron of accuracy or something resolution, and then you can get the by touching the things you can get, but these are called the non-contact type of things. So, you do not require any type of additional setup into the machine. So, let me stop it here, then we will continue this lecture in the next class. Thank you very much.